What we're going to do today is take some notes over section 6.2, which is about one-to-one functions and inverse functions. So you probably remember that in order for something to be a function, each input, which is an x value, can only have one output, which is a y value. Those functions have to pass the vertical line test, which means that if you draw any vertical line, it can intersect the graph in only one place. So what's different about a one-to-one function is, first of all, it must be a function. So it still has to do each input can only have one output and must pass the vertical line test. So in order to be a one-to-one function, you first have to be a function. But then to be one-to-one, each output, which is the y values, can have only one input, which is an x value. So one-to-one functions must pass the horizontal line test and the vertical line test. So it's a lot easier to see if you have a one-to-one function by looking at the graph than it is algebraically. But let's look at these two, what we call mapping diagrams. So as you can see, this is, kind of about, we've got Ross, Joey, Chandler, and Bob, and then these are our inputs, and then our outputs are Rachel, Phoebe, Monica, and Sue. So we want to see, first of all, is this a function? And then second, is it one-to-one? So in a function, each input value, which is an x, can only go to one output value, which is a y. So Ross goes to 1, Joey goes to 1, Chandler goes to 1, Bob goes to 1. So is it a function? Yes. Each input only goes to one output. Then is it a one-to-one function? So in a one-to-one function, each output can only be paired with one input. So Rachel goes to Joey, Phoebe goes to Ross, Monica goes to Chandler, Sue goes to Bob. So it is one-to-one because each output goes to only one input. Okay, let's look at this mapping diagram. It's got the same outputs and inputs, but then different map. So here we have our inputs, here we have our outputs. So is this a function? Ross goes to 1, Joey goes to 1, Chandler goes to 1, Bob goes to 1. So yes, it is one-to-one. Let's see if it is a function. Let's see if it's now one-to-one. Rachel only matches with Ross, Sue matches with Joey, Sue also matches with Bob. So is it one-to-one? No, because one of the outputs, namely being Sue, pairs with more than one input. So that is not a one-to-one function. Now let's talk about inverses, because that's the whole reason we care about functions being one-to-one. In an inverse, the x's and the y's switch places. Remember, the x's are the domain values and the y's are the range values. So when you switch the x and the y's, then you also switch the domains and the ranges. So the domain of the function is the same as the range of the inverse of f of x. This is the notation for the inverse. F to the negative 1 of x is, we don't say f to the negative 1, we just say the inverse function. So then since we switch the x's and the y's, the range of f of x becomes the domain of the inverse function. So that has some interesting applications when it comes to graphs. So let's look at some of these situations. If our function has the point 321, then the inverse function has the point, remember that the x's and the y's switch place, so that would be 21, 3. Okay? If the inverse function, this is the inverse function to g of x, the inverse function at 32 is equal to 5, then g at 5 would be equal to what? So basically, this gives us on the inverse function an ordered pair 32, 5. So the input for the inverse function is 32, the output is 5. But then on g of x, remember that the x's and the y's switch places. So this would be 532. So now my input is 5, which matches that, and my output is 32. So g of 5 would be 32. Let's look at some graphs. Here's looks like a square root function. F inverse of 2 would be equal to what? Well, on the inverse function, we have, on the function, we have a couple of ordered pairs labeled. This one would be 4, 2, and this one would be 1, 1. So if the original function has the ordered pair 4, 2, then the inverse function would have the ordered pair 2, 4. So in other words, this is saying if f inverse of x gives me 2, well, I'm wanting 2 to go in the input and I want to know the output, then f of x would have a y value of 2. So another way to think of this is that I'm wanting on f inverse of x, I have 2 question mark. Well, I have that written here. Then I'm asking on f of x, that would be what 2. So the ordered pair that I have labeled on there is 4, 2. So it would be f of 2 would be 4. Now we can also find the inverse graphically. I kind of planned to have us draw this in there, but it's already on our paper, so we'll just kind of talk our way through it. To find an inverse, what we do is we switch the x and the y coordinates, which makes the inverses be reflections across the line y equals x. So you can see this point right here, 1, 3, is straight across the line y equals x from the point on the inverse function, 3, 1. So here's our function. The function would be kind of the purple one. Then the inverse function would be kind of the green one. So this is f inverse of x. So each ordered pair switches the x and the y's. So 0, 2 would become 2, 0. Negative 1, 0 becomes 0, negative 1. 3, 4 becomes 4, 3. What's interesting is the places where it crosses the line y equals x, those two functions intersect each other. So negative 2, when you switch negative 2, it stays negative 2. So that ordered pair will be right on that line. Same with this one right here. Whatever it is, we don't have it labeled. It looks like it might be 3, 3. When you switch it, it's going to stay 3, 3. So right where your function intersects the line y equals x, the inverse will also intersect the line y equals x. So if I gave you the graph of f of x like this, you could, even with no ordered pairs sketched, you could graph f inverse of x, because we're just going to go straight across from each of these points. So this point that's right here on f of x should be right about here on f inverse. And then since it appears that my function has a horizontal asymptote, that would make my inverse function have a vertical asymptote. So they should look like mirror images across that line y equals x. So what happens, or what's the importance that I mentioned earlier about when a function is not one-to-one? So if you look at the one we just drew, f of x is a function because it passes the vertical line test. It's also one-to-one because it passes the horizontal line test. And what you notice is that the inverse is also a one-to-one function. But when your function is not one-to-one originally, then what happens when you switch the x's and the y's, so here's my function, f of x equals x squared. Here's my inverse function. It's just reflected across that line y equals x. This inverse function, this inverse is not a function. So if we look at our original function, the domain was negative infinity to infinity, and its range was 0 to infinity. If you look at the inverse function, when we switch the domain and the range, the domain would be 0 to infinity, and the range would be negative infinity to infinity. But since that inverse is not a function, then what we can do is we can force it to be a function by restricting the original function's domain. So if we restrict the original function's domain, then that will make the inverse be a function. So let's look at kind of getting rid of part of that original function. So what I'm going to do is I'm just going to squiggle out this part of the graph. And so I'm going to take my function, my f of x. The domain was negative infinity to infinity, but that means that f inverse is not a function. So we want f inverse to be a function, so we are going to restrict f of x's domain to 0 to infinity. And that is going to make f inverse a function. How does that happen? Well, I scribbled out this part of my original function. How does that impact my inverse function? This part is reflected straight across to here. This point is reflected to here. This point is reflected to here. So what that's going to do is by getting rid of that part of this function, it gets rid of this part of the inverse function. So now this part would not be here anymore, which makes f inverse into a function. So I should label that up here. So now f of x is x squared with a restricted domain. So now I'm going to restrict my domain. Instead of negative infinity to infinity, I'm going to restrict it to 0 to infinity so that my inverse will be a function. Now there is a way for us to verify that two functions, if we have the equations for them, like this example, we can verify that they are inverses. So I think I'll highlight that. To verify that two functions are inverses, we're going to do the composition of functions. Now, inverse functions are kind of like inverse operations. Like if I started with x and I took the square root of it and then I squared it, because those are inverse operations, they undo each other and I just end up with x. Well, inverse functions work the same way. If I take my x and I do f inverse to it, and then I take the output of that and I do f to it, then I get back my original value of x, or whatever number I put in there. Same thing here. If I put x into my function f, and then I put its output into the inverse function, the inverse is going to undo whatever I did with the function, and I'll end up with x. So we can use that to verify that f and f inverse are functions. So we'll do f circle f inverse of x, and we'll see that we get out regular x. So f circle f inverse means I'm taking the function f and I'm putting in x plus 3 over 5. So here's my x where I'm putting that in. So that will be 5 times x plus 3 over 5, subtract 3. Now when I multiply 5 times x plus 3 over 5, what happens is the multiply by 5 and divide by 5, those cancel. So now I have just x plus 3 minus 3, and x plus 3 minus 3 equals x. So we've verified it that direction. Then we'll do f inverse circle f of x, so that I'm going to do the inverse function and replace the x right here with 5x minus 3. So that will be 5x minus 3 plus 3 divided by 5. 5x minus 3 plus 3 is just 5x over 5. 5x over 5, the 5s are going to cancel, and I'm going to be left with x. So we have verified that both of those directions work, f circle f inverse and f inverse circle f. So we know that that function and its inverse are as shown. Let's look at a couple more examples. Are f of x and g of x inverses? So we will do f circle g and g circle f and see if they come out to be inverses. Okay, so we're going to do f circle g of x, which means I'm doing f of cube root of x plus 8. So in f of x, I'm going to be replacing this x with that function instead. So I'm going to have cube root of x plus 8 cubed, subtract 8. Well, when you cube a cube root, those operations undo each other. So that's just going to leave me x plus 8 minus 8, which equals x. So that part we're good with. And then we will also check g circle f of x, which means I'm doing g of f of x. So replacing this x right here with x cubed minus 8. So that is going to be the cube root of x cubed minus 8 plus 8. X cubed minus 8 plus 8 would just be the cube root of x cubed, and the cube root of x cubed is x. So we have checked it both ways, so we can say yes, they are inverses. Okay, let's do this one right here. Now, why do you suppose it says x minus 2 squared, comma, x is greater than or equal to 2? X minus 2 squared is a parabola that's shifted to the right 2. So x minus 2 squared would look something like this. And then g of x is the square root of x plus 2, which is an eyebrow function shifted up 2. So it would look something like this, which is not the inverse of this entire parabola. It is the inverse of this part of the parabola. So you can see that by restricting the domain, that gets rid of that entire half. So now these two functions are both one-to-one, and they can both be functions, and we'll check to see if they're inverses. Graphically, it looks like they are, so I won't be surprised if we find that they are. So we'll just test them. F circle g of x means I'm taking f of x and replacing the x with g of x, which is square root of x plus 2. So in f of x, which is x subtract 2 squared, so I'm replacing the x with the square root of x plus 2, so and then minus 2 squared, which would be the plus 2 and minus 2 cancel, so square root of x squared, which would leave me x. So it worked that direction, and then we'll go the other way. G circle f of x, so I'm going to do g of my f of x. F of x is x minus 2 in parentheses squared. So g of x is square root of x. So I'm replacing that x with this stuff. So I'll have square root of this stuff here, x minus 2 squared, plus 2. Now when you square root something that is squared, that just undoes each other and leaves me with x minus 2. And then I still have plus 2 out here. X minus 2 plus 2 is just X, which means that works as well. So yes, they are inverses. Now, if they were not inverses, we would not end up just with X at the end. We'd end up with something different from X. So if it's anything other than just an X, you'd say no, they're not inverses. Okay, now to find an inverse, we also need to be able to find an inverse if we're given a function. Now, I'll tell you that you can't find inverses for every function, but you won't be asked to find one if you don't have the ability to do that. So to find an inverse algebraically, what you're going to do is you want to start by writing the problem as y equals instead of f of x equals. So just when you copy the problem down, don't use the function notation, just use y. Then you're literally going to switch all the x's, like you're going to turn every x that you see into a y and turn the y into an x. And then you're going to solve for y, just like you would if you're putting something in slope-intercept form, kind of. You want to isolate the y, and then when you're done with that, you just rewrite it with f inverse of x instead of the y equals. Remember, in finding domain and range, the domain of the function is the same as the range of the inverse, and the range of the inverse is the same as the domain, the range of the function is the same as the domain of the inverse. So mainly what we have been able to find more easily is the domains. So usually what I will do is find the domain of the original function and the domain of the inverse function, and then that gives me the two ranges. Since domain is easier to find, that's usually my strategy. Okay, so let's do a couple of examples for finding inverses algebraically. Here's our function, f of x equals x minus 1 over 5. So when you write this down, when you're working through problems, just write it as y equals x minus 1 over 5 instead of f of x. And then what we're going to do is switch x's and y's. So that is now going to become, instead of a y, that's an x, and instead of an x, that's a y. And then we're going to solve for y. So first off, I will multiply both sides by 5. So then I'll have 5x equals y minus 1. Then add add 1 to both sides. So I get y equals 5x plus 1. And then that's going to be my inverse. So f inverse would be 5x plus 1. I just replace the y with the f inverse notation. And what I want to do is find the domain and range for each. So I'm going to start with my domain for my original function. The domain for the original function should be all real numbers because I don't have any variables in the denominator and I don't have any even index radicals. So the domain here is negative infinity to infinity. And that gives me the range for my inverse function, negative infinity to infinity. Okay. Then I want to find the domain for my inverse function. And again, well, this would be a line. So is the other one. But there are no variables in the denominator and there are no variables inside even index radicals. So this domain would also be negative infinity to infinity. And that is going to give me my range for my original function. So negative infinity to infinity. Okay, let's practice doing that with a little bit more complicated function. So we're going to do the same, it's going to be the same idea. So y equals 3x plus 2 over x minus 5. And let's go ahead and start by getting the domain of the function, which would be, I'll use set builder notation, x such that, what can x not equal when I have x minus 5 in the denominator? X would not be able to equal 5. Now, I already know the range for my inverse function. So I'm just going to go all the way down to the bottom here and say that the range for my inverse function would be, now it's not x cannot equal 5 because now it's a range. So ranges are y's. So the range would be y's such that y cannot equal 5. Once we find our inverse function's domain, then we will take it up here and write that as the range of our original function. So I've already got that planned out. Okay, so to get to my inverse, first I will switch the x's and y's. So I have the y becomes an x, and this x becomes a y, so does this x. Now I need to solve for y. So this one's a little bit more complicated. That's good. We'll start out, though, by multiplying both sides by y minus 5. So that's going to allow me to cancel this y minus 5 with that y minus 5. And I think I will go ahead and distribute this x into that parenthesis. So now I have xy minus 5x equals 3y plus 2. Now we have to solve for y. That's our goal. But the problem is we have more than one term that has a y in it. We've seen this before. I will remind you of the strategy that we've used in the past. What we need to do is get all terms with y on the same side. So I will start by, I'll probably subtract the 3y to this side. So then I'll have xy minus 3y equals, and then I also need to move anything that doesn't have a y to the other side as well. So I'll add 5x over to this side. So now on the right side, I have 5x plus 2. Okay, next step is going to be to factor out y. It's like a GCF. It actually is a GCF. We're just going to factor out a y. So I see that I have a y in this term and a y in this term. So I just bring it to the front, y times, and then that leaves me with x minus 3 in the parentheses, and then equals 5x plus 2. And then the next thing we'll do is divide both sides by the parentheses. So now I'm just going to divide both sides by x minus 3. And that's going to give me y equals 5x plus 2 over x minus 3. And then this is my inverse function. Remember, we needed to rewrite it with inverse function notation. So the inverse function would be 5x plus 2 over x minus 3. And now we can pretty easily get the domain. Remember, you would set the denominator not equal to 0. So we would get that x cannot equal 3. So that will be our domain, x such that x cannot equal 3. And then remember that that little tidbit also tells us our range for the original function, except for range is y values. So our range would be y such that y cannot equal 3. Okay, should we do another example? Ooh, I knew you'd want to. So let's do this one. Let's do this one. Okay, our function is x squared minus 4 over 2x squared. Notice that we have a domain restriction that x has to be greater than 0. So we don't have too much messing around to do with finding the domain for the function. The domain for the function would be 0 to infinity. Or if you're using set builder notation, it would be x such that x is greater than 0. And the range we don't know yet. We will know the range once we get the inverse function. I'll just do this. I'll just leave a space for the inverse function and its domain. And then I know the range of the inverse function. The range of the inverse function is going to be the same as this domain, so 0 to infinity. Or if you're in set builder notation, we'd have y such that y is greater than 0. Okay, moving on. So let's find our inverse. So our original function was y equals x squared minus 4 over 2x squared. Then to find the inverse, we're going to switch the x's and the y's. So that gives me x equals y squared minus 4 over 2y squared. And now we've got to solve for y. So we'll start kind of like we did the other ones that were rational functions by multiplying both sides by 2y squared to get that variable out of the denominator. So now we have, I'm going to put it like 2xy squared equals y squared minus 4. Now this is kind of similar to the one we just did where you have more than one term that has y's in it. So we're going to go ahead and kind of use the same strategy, similar strategy. We'll subtract that y squared over to the left side. So we have 2xy squared minus y squared equals negative 4. And then we see that there is a GCF of y squared here. So we're going to factor that out. So now we'll have y squared equals, oh, I am just kidding, y squared times, take off that y squared, leaves us with 2x, divide that by y squared minus 1 equals negative 4. And then, like we did before, divide both sides by that parenthesis. So now we have y squared equals negative 4 over 2x minus 1. Now, our job is to get y by itself, not y squared by itself. So we are going to have to take the square root of both sides so that we have y squared equals. Remember that when you take the square root of both sides, what do we have to always remember to put? That is right. We have to remember the plus or minus out in front. Now we're going to pause right there because right up here in our range, we restricted y to be greater than 0. So when we look at our plus and minus here, in order for y to be greater than 0, we are only going to worry about the plus part, and the minus part we're going to ignore. So we will ignore the negative part of that square root, this negative part, since we had that range restriction. So our y, oh, that's not y squared. Our y is just going to be the square root of negative 4 over 2x minus 1. So that right there is our inverse function, is going to be negative 4 over 2x minus 1. I'm going to make that look a little bit different, though, because I'm a little bit freaked out by that negative 4 inside a radical. So I'm going to just multiply the top and bottom, the numerator and denominator, both by negative 1 inside that radical. So what that's going to give me is, now the numerator is going to be positive 4, which makes me feel more comfortable. And the denominator is going to be negative 2x plus 1. Then I can think of that. Remember when we have radicals with a numerator and denominator, we can think of it like two separate radicals. So that's like square root of 4 over square root of negative 2x plus 1. So I can simplify the 4. So now y is going to be 2 over square root of negative 2x plus 1. Okay, that's going to be my final inverse function. So I'm going to write that up here where I left a space for it. So So f inverse will be 2 over square root of 1 minus 2x, or negative 2x plus 1. That's the same thing. Whichever one you feel happier about, you can use 1 minus 2x or negative 2x plus 1. Now let's figure out the domain for our inverse function. The domain here has two issues. One issue is that the denominator cannot equal 0. The other issue is that we have a radical that has variables in it. So normally we would set the radicand to be greater than or equal to 0, but we also know that the denominator cannot equal 0. So we'll just combine those two ideas and set our radicand greater than 0 instead of greater than or equal to. So our radicand will be negative 2x plus 1. Negative 2x plus 1 can be greater than 0. And then subtract 1. Negative 2x has to be greater than negative 1. Divide both sides by negative 2. And that leaves us with x on this side and positive 1/2 on this side. Remember that when you divide both sides by a negative, you have to reverse the inequality. So this will be x is less than 1/2. So think about a number line. We have 1/2 less than, not equal to, so open circle, and less than. So that would be negative infinity to 1/2 for our domain. Negative infinity to 1/2 with a parenthesis because it was an open circle, which makes the range here the same thing, negative infinity to 1/2. And if we're using set builder, that would be x such that x is less than 1/2 on the domain, and on the range that would be y such that y is less than 1/2